Okay, I want to continue partially where we left off before. That is looking at these what's called thermochemical equations. Here at the bottom of the screen, you'll see an equation that says CH4, also known as methane, or 1 mole of methane, and 2 moles of oxygen makes 1 mole of carbon dioxide and 2 moles of water, H2O. And delta H is equal to negative 890.4 kilojoules. What that negative 890.4 kilojoules means, oops, let me go back. Sorry. Okay, what does negative 890.4 kilojoules means? It means that number, negative means exothermic, that 890 kilojoules of heat is given off for every 1 mole of this. In fact, it's written here. 890 kilojoules of heat are released for every 1 mole of methane, CH4, that's combusted at this temperature and pressure. That's actually not too relevant here. By the way, we're always going to assume for this chapter that this is just done at normal pressure, atmospheric pressure, 1 atmosphere, and 25 degrees Celsius is pretty much room temperature. So 1 mole of methane and 2 moles of oxygen makes 1 mole of carbon dioxide, 2 moles of water. This is a balanced equation, and it gives off 890 kilojoules of heat. Okay, negative, again, just a reminder, means exothermic. Positive means endothermic. Okay, those stoichiometric coefficients are always referred to number of moles of substance. So here, 1 mole of ice, H2O solid, makes 1 mole of water, H2O liquid. Delta H is positive 6.01 kilojoules. Positive means endothermic. It absorbs heat. In fact, to melt ice, to turn ice into water, solid, H2O, liquid H2O, to turn ice into water, it needs to absorb heat, energy. It absorbs 6 kilojoules of energy specifically. So to melt 1 mole ice, it requires 6 kilojoules of energy. Not surprisingly, this is going to come up on the slide anyways later, but to melt 2 moles of ice, how much heat do you think you need? To melt 1 mole of ice, to melt 1 mole of ice, it'll take 6 kilojoules of heat, 6.01. To melt 2 moles of ice, it would be 2 times 6.01. To melt 3 moles of ice, it'll be 3 times 6.01. To melt X moles of ice, it'll be X times 6.01. So stoichiometric coefficients always refer to number of moles of substances. This is coefficient 1 and 1. But if there's a coefficient 2 here, that means to melt 2 moles of ice, it will require, whatever that number says. If you ever reverse a reaction, we change the signs of delta H. Here's the same equation, just flipped. Solid, liquid, liquid, solid. We flipped it. And whenever you do that, you change the sign from positive to negative. What that means is if you need to absorb 6 kilojoules of heat to melt 1 mole ice, to freeze 1 mole of water, it needs to negative exothermic. It needs to give off 6 kilojoules of heat. So to turn liquid water into solid ice, to turn liquid water into solid ice, it needs to give off 6.01 kilojoules of heat. So when we flip an equation, reverse it, we always, what we do is we change the sign. Okay, so notice liquid here, solid there. Before it was solid liquid. And this is what I was just saying earlier. If we multiply both sides of the equation by a factor n, delta H must be multiplied by a factor n. So this is 1 mole of water turning to 1 mole ice turning to 1 mole water gives off 6 kilojoules of heat. So if I had 2 moles of ice turning to 2 moles of water, the amount of heat it needs to absorb will be 2 times 6.01, or 12. Okay, so 3 sig figs. Okay, 12 kilojoules of heat. Okay, so one other thing about thermochemical equations. The physical states of all reactants and products must be specified in the thermochemical equation. What that means is here, solids and liquids, they must be in the equation. It's important that the state of matter must be in there. Why? Going back to that last slide, notice solid, liquid, liquid, solid. So if we flipped it, these numbers would, literally flip. So this is here solid and liquid. If it was solid to gas or liquid to gas, this would be a completely different number. I don't know what the number is off the top of my head, but that would not be the amount of energy. So the state of matter does matter in this case. Here, liquid to gas, water to steam, to gaseous steam. It takes 44 kilojoules of energy. It absorbs 44 kilojoules of energy to turn water into steam. Only it requires 6 kilojoules of energy to melt 1 mole of ice into water. So the state of matter here, liquid to gas, does matter. Okay, let's look at another sample question here. How much heat is evolved when 266 grams of white phosphorus, P4, burns in air? Right now, you'll be given the equation. This is not something that you would have to memorize. This has to be given. And what does this equation say? It says 1 mole of P4, phosphorus, and 5 moles of oxygen, O2, turns into 1 mole of P4O10, and delta H is negative 3013. But negative means exothermic. It's going to give off 3013 kilojoules of heat for every 1 mole of phosphorus, 5 moles of oxygen, and 1 mole of P4O10. Well, I don't have 1 mole of P4. I have 266 grams of it. But if I have grams, I can change grams to moles. I don't know, you hopefully remember from last semester, how do we change grams to moles? We have to find a molar mass of P4. That is 4 times the molar mass of phosphorus on a periodic table. They're not numbers to memorize. Actually, I don't remember phosphorus off the top of my head, but 4 times phosphorus on a periodic table is 123.9. Again, the molar mass of P4 from the periodic table. Then you have moles. Again, I know currently 1 mole of P4 is 3013 kilojoules of heat. 1 mole of P4 is 3013 kilojoules of heat. Why not negative? I'll come back to that. But I mean, you technically could put it in, but it's not really necessary. Notice grams and grams cancel, moles and moles cancel. So the only thing you have left are kilojoules. The answer is going to be 266 times 3013 divided by 123.9, or you get 6470 kilojoules of heat. Now, why didn't I include the negative? You can, but the question is how much heat is given off? Negative means it gives off heat. I already know it's giving off heat. Okay, the negative is more like a direction. I know it's going out. The question is just how much. So you can almost say the absolute value of it. But it's 6470 kilojoules of heat to 3 sig figs. There is one other thing I wanted to mention. Okay, so this thing is just on, what do you call this thing? PowerPoint. But I just want to also mention that if there were a coefficient, I'm going to put one in right now. Let's say there's a coefficient 3 there. I know that's not balanced anymore, but let's say there's a coefficient 3 here. This would mean 3 moles of phosphorus gives 3000 kilojoules heat. I would also have to change this to a coefficient of 3, meaning the answer would be 6470 divided by 3 at the end. If there was a coefficient 5 here, the math would also change, because this would mean 5 moles of P4 is 6470 kilojoules of heat. Sorry, 5 moles of P4 is 3013 kilojoules of heat. So it would be 6470 divided by 5. So this one had a coefficient of 1, but what I was just saying is if there was a different coefficient, it would change the answer. Okay, so I would actually have to take into that account. This one had a coefficient of 1, so I'm going to put a 1 back. Actually, we don't write 1s there. So if there was a 1 there, then, and it was originally, that's what this is. Okay, so hopefully there will be other sample problems with this, but this is just the beginning of thermal chemistry.